Yeah.
Okay, so yeah, okay, maybe let's continue. So we have the definition anyway. So we have definition of the reduced groupoid system algebra. So the question is so when this guy has nice properties. So like the when this guy is suppose we want to classify it. So when it's simple, unital, separable, nuclear, and z stable, right? So I should say so by result of the two. So if it is a nuclear, so if and only if your groupoid is amenable, and in this case it satisfies the UCT automatically. So you don't have to worry about the UCT part. So this full condition are easy to.
Sorry, I have a question. Automatically is by result of two, right?
Yeah.
Published only in French.
Possibly, yeah, maybe, yeah, okay. So anyway, so for these four conditions are quite easy to obtain. So I will write it as a fact. Okay, fact one. So this guy is unital. Okay, if you are unit space, your set of points is compact. Yeah. And second, so this guy is separable. Okay. So if your groupoid is second countable, okay. And third one, so this guy is simple. If your groupoid is minimal and topological pretty simple, but if you have the second countable, so actually, so you have effective. Okay, in the sense that so minimal is minimality is like is the similar type of the conditions in the dynamical systems. Okay, so let me explain here. What? For groups, yeah, that's a very good question. So your groups can never be effective. So there's no freeness. So that's why the system simplicity is a very good question for groups, because you have to find some different ways. Yeah, but in our case, we only care about, I mean, that your unit space is infinite. It will never be a group case. Okay. So the definition. So the G is minimal if the all base. Okay. So all base. Maybe I should write in this way, all base. So GU, okay, it's a dense in G0. Okay, so for any U in G0, and G is effective of a topological point simple, maybe, yeah, because we do not assume that, always assume that it is second countable. So topological. Yeah, it's a topological point simple. If the unit with a trivial stabilizer is dense. Yeah. Here I use the GUU. Okay, just equal U itself. Okay, it's dense. Where your GUU is exactly all possible errors that as the source and the range are U. Okay, so stabilizers. Okay, trivial. So in this case, your cis algebras is simple. And so 4. So your cis algebra is nuclear. If and only if your G is topologically amenable. By a result of 2. And in this case, you are this guy satisfies the UCT. Yeah. So I should mention that. So if your groupoid is just a group, so the topological amenability is equivalent to the amenability of the group. But in general, like even for the dynamical systems, so this does not imply that your acting group is amenable. It just implies that your action is topological amenable. Okay, so for example, even for the purely infinite case, okay, suppose you are free group acting on the Gromov boundary, so your action is still amenable, but your acting group is a free group, which is not amenable. Okay, but in that case, you still obtain that your groupoid cis algebra is nuclear. Okay. So okay, so we have some natural conditions. Oh, I can do this first.
Why can't you use the bottom board?
What? This one? Oh, this is a board? Oh, I thought it's a wall.
Both. In some places, in some places, the wall is also the screen for projection.
Oh, yeah, sure. And even I know a place the wall is actually a board. Yeah, University of Houston. Yeah. Anyway, yeah. So we have natural conditions for groupoid so that the reduced cis algebras satisfying the simplicity, unitality, separability, and nuclearity. So the only the problem or difficult job is to show this stability. Okay.
I think by now you don't need to say unital. You'd be non-unital classification is
Yeah.
is under control.
Yeah. So, but
almost all of it public.
But actually, for our job, maybe we need the space, the underlying space is compact. So for the locally compact case, I don't think we have a way to deal with it.
To do which?
So
Because to answer these questions, to decide the other properties.
Yeah, what I mean is that so if the cis algebra is not unital, so in the case that your underlying space is just locally compact instead of.
Well, okay, but the real line is locally compact, but I'm not quite okay. You know, you're scaring. You're giving a scary story without really explaining what we should be scared of.
Well, I think Shin means that the result for Z stability is in the unital case, proven in the unital.
Yeah, in our paper.
No, but no, recently there's a non-unital, very recently by Schwann norm, there's a non-unital Z stable theorem.
Yeah, that's true. What I mean is that so in our paper, in the setting of the groupoid cis algebra, we cannot deal with the non-unital case. That's what I mean. So maybe in some cases, in the purely infinite cases, we can deal with the stability, but in general, so especially for stably finite case, for stably finite groupoid cis algebra, we do not know how to do that.
I'm not quite sure what it is you can't do. You have a groupoid C-style algebra, non-unital, and the question is, I mean, you haven't said in the unital case what the criterion is for these.
Yes, exactly. So because we need that we need tracial states. Yeah, we need some measures on the unit space to do this.
Well, okay, but there's a theory of unbounded traces.
Yes, that could be true, but I mean at this moment, so I and Jian Chao do not have a time to think about it. That could be true. Yeah, that could be true. So to
Anyway,
generalize.
It seems to me the objections you are mentioning also refer to the general question. They have a non-unital C-square algebra, nuclear C-square algebra. Maybe it doesn't have to be Euclid. It's a quite weak condition. Non-unital and then you tensor with the well. Okay, I'm not quite sure what the theorem is you're talking about. You're leading up. But
Yeah. So I will.
you know, there's a school of thought that says all theorems should be they should wait till the very, very, very end to be stated. But I learned when I was studying that it was the opposite.
Okay.
And,
Okay.
Yeah. Kaplanski once gave a colloquium here.
Yeah.
And he said this colloquium is going to have two parts. This talk is going to have two parts. The first 5 minutes, everyone will understand it. And the next 5 minutes, the next hour, no one will understand. He didn't quite say it like that, but what he said was essentially just an application of the first 5 minutes. In other words, the main result, the first 5 minutes.
Okay. Yeah. So maybe let me give you our main result. So and I will explain. So the items we will use. So the theorem. So by me and Jian Chao. Okay. So let your groupoid be locally compact cost of itself with this guy is compact. Yeah. Of course, you have to assume minimal. Actually, don't have to assume topological simple because our notion implying this. Yeah, and the new notion that I will explain later is almost elementary. So suppose we have this. Okay, it's you are reduce the groupoid CC algebra is spatially okay. That's important. This stable. Okay, so and if you add the assumption that your groupoid is is amenable, okay, then you obtain the nuclearity of your CC algebra, then you can erase the trivially. So that's my theorem here, and we have seen that. So how the minimality.
Is it just to check? Is it also a if and only if statement or no?
No, it's not if and if. That's too strong. Actually, we have a counter example.
All of those previous ones, I think, are. Oh, yeah.
No, this one, no. This one, no.
Really?
No. You have to maybe add your groupoid is minimal.
Oh, right. Okay.
Yeah. So actually, we have counter example here. So yeah. So actually, so we have seen that how minimal and other compact, how this affect this theorem by this, right? So, sorry, I should add some this stable and the unital, right? Or maybe so second countable, yeah. Separable. Yeah. Then what? No, right? We're good. Okay. So the almost elementary, okay, just implying trivial stability. So that's a point. So and we will see how it works. Okay. But before
what would elementary mean?
Means somehow it contains matrix structure.
Contains.
Yeah, that means you can find some sub groupoid, which somehow looks like matrix. of the
Yeah, trivial.
yeah in your original groupoid.
That's what. Okay, but is that you're doing it with almost?
Yeah, that means you can
Anyway, I'm asking without the almost. What is it without the almost?
without with
What's that? That means when it is a matrix algebra.
yeah, it's just somehow just the matrix of the continuous functions exactly this way. I will explain next exactly. Yeah.
When you know it's standard terminology for algebras. Elementary means it's a compact operators on some Hilbert space.
Yeah.
That's for C-star algebra.
Yeah.
No, but I don't think almost elementary has been defined for a C-star algebra.
No, I don't think so.
Well, but maybe if you're proposing a definition for a groupoid, then maybe at the same time you're proposing a definition for a C-star algebra.
Oh yeah, that's a good idea. Yeah.
So what would the definition be for a C-star algebra?
And I feel that it's just like you can somehow by using in some way you just use the matrix of the functions to approximate it in some way. I don't know. So
I'm not quite.
that's a one way.
I'm not quite sure what M and C of X.
I'm some yeah.
But are you also, I forgot, is it also okay if it's K tensor? Is then allowed to be infinity?
You mean
Okay, but you know.
Oh, no.
I mean finite dimensional matrix.
Elementary for a C-star algebra means Mn of the complex number.
Yes, exactly. But it's just the name. It's just like you have a structure.
We're trying to find out
Yeah.
what you're talking about. And so if you say something like C of X, that's to me, that's not an elementary C-star algebra.
No, it's
It's what's called a homogeneous.
yes. Yeah, but elementary here it just means it has somehow you have a matrix structure. I'm not saying it's
Well,
exactly a
this is
matrix.
an almost elementary C-star algebra. Mn, C.
In our definition, yes.
Well, okay.
Yeah.
Anyway, if you're introducing the terminology for groupoids, it would seem to me to make sense to introduce it in a parallel way, completely parallel way. to algebra.
Oh, yes, that's
And if but sometimes if you do that, the terminology will already exist for the C-star algebra. Like here, this is often just called a homogeneous. So maybe it should be called maybe when you say almost elementary groupoid, maybe
almost a homogeneous.
maybe a more familiar terminology would be homogeneous.
Most homogeneous, almost homogeneous.
No, just exactly homogeneous. Oh, this is.
But this is not exactly the algebra we obtain. Actually, we use this to approximate.
Look, this is not an elementary C-star algebra. This is an almost elementary C-star algebra.
The groupoid underlying this algebra satisfying our condition.
Well,
Yeah,
yes,
almost
but then since if almost elementary for the algebra is synonymous with homogeneous, then it should be the same for the groupoid. There should be something called a homogeneous groupoid, and which means that it's.
Yeah, but what I'm saying is that so this is a very special case in our definition. It could be, I mean, so like the many cross product. I mean the transformation groupoid of the cross product also.
So what's the most general C-star algebra of an almost elementary groupoid? Well, that's this theorem. That applies to this theorem. In fact, almost elementary is quite general.
Yeah, it's much more general than this. I mean, specific form. And I will.
I think it would have been better if it was called almost homogeneous, because right.
Do you have any restrictions on the dimension of X?
No.
Even in your group, don't you need to assume the dimension of X is bounded?
No.
If the dimension of X is bounded by 1, then that some kind of makes sense. That will be the order zero map image of.
Yeah, the point is that you can use the order zero map. So embed somehow to embedding or to map your matrix into this algebra. So that's the point. So almost elementary. So at first we call it almost finite. It's just to borrow the notion, almost finiteness. So borrowed from the David Kerr and Matsui. But as fact, so you suggest to Jian Chao that is not a good name because there's no finiteness here. So then we changed to almost elementary.
Did I do that?
Jian Chao told me the story.
So you didn't finish the chapter, then it's your fault.
I don't
You
remember.
could have pushed for a better name.
So Jian Chao told me that you said there's no finiteness here. So
Okay, what's an example? What's a typical example of an almost elementary?
so maybe the trivial example is like the integers z acting on the counter side. So then the transformation groupoid, the underlying transformation groupoid is almost elementary. And if you want
almost which?
almost elementary,
Almost elementary.
and if you want some like non-amenable group action, like the free group acting on the Gromov boundary, so it is also almost elementary. And also some Telling groupoid, especially the Telling
Okay,
groupoid.
that's something that's not almost elementary.
So far we don't have such an example.
You mean every groupoid might be almost?
No. Oh yeah, we have an example. So actually, it's done by very recently by Matthew Joseph. He construct. I mean, a lot. I forget the name. A lot heuristic action by using profinite action to show that it is not almost finite. But in that case, almost finite is equivalent to our almost elementary. So that means that groupoid is not almost elementary.
It was a bit confusing because elementary is also used in connection with amenable groups. An elementary amenable group is a certain.
Yes, that's right. But so elementary maybe here, so there are something common, just like it is elementary. It is not so complicated. It's just elementary.
Do you have time to give the definition?
Yeah, sure. I will give a definition. So actually,
Can you- My principle is that before you write something on the blackboard, you should say it.
okay, yeah.
And then it's only if it can be said that it should be written on the blackboard.
Yeah, okay. I will give the almost elementary. I mean, the definition of the almost elementariness in a moment. So
In a moment, again, if you-
yeah, at this moment, okay, I will give the definition. Maybe let me keep this. Okay, let me keep this.
I prefer the past. The difference in our age.
So let's first. So I should say the definition is due to the Nakrashevich. Okay, he defined multi sections. It's just nothing but a bunch of the bisections. Okay, so you have a bisections, ij in some index at I. Okay, such that so the S V ij is the Vjj. Okay, and the range of the Vij is just the Vii. Okay, and so Vij times Vkj is exactly Vik. Okay, so you can see the matrix structure here. Right? So, and then the Vii is just okay, 1, 2, 3. So I just some set contained in the unit set. Okay, so for any I in I, and they are destroyed. So Vii intersect with Vjj. If I is not equal j, it's empty. Okay, so that means suppose this is your G0, the underlying space, and you have something like that. Okay, the V11, V22, V33, V44, and the bisection just connect them. It's like a tube. Okay, like a tube to connect them. Okay, so and this actually give us a groupoid, a subgroupoid, right? So the groupoid H, okay, you just union them together. I. So it's called actually. So this is not our name. It's called elementary groupoid. So that's how the elementary comes from. So elementary groupoid. And actually, you don't have to consider only one multisection, right? You can consider a bunch of multisection. So provided that they are disjoint.
This one is still elementary. In this sense.
You mean this one?
Yeah.
Yeah, exactly.
Okay, so with the groupoid terminology is completely different from the algebra terminology.
Yeah. So I believe so. This comes from the Renault. I forget. Yeah.
Wait,
Renault. No.
Well, I'm not sure.
So yeah, but this name it definitely not. We do not use this name. Okay, this is not. We are not the first. So they call it elementary groupoid. So then, of course, so as I said, you can consider a collection of multi-sections so that you have
Wait, I'm actually sorry. I'm a bit confused. Though. Is the groupoid of that
exactly this.
exactly that?
Yeah. So especially when your axis.
For x, like if it's some space, how do you?
So okay. So here, suppose. Suppose you are all via a open, compact open. Okay.
Sure.
Then you can just change the x by VII any VII you want. So the groupoid is this algebra of that
No,
guy.
So this algebra corresponds to the groupoid where you just have like n copies. Well, you just have x, and then you have n copies of your space, right? And then you have a bunch of these.
So you have n copies of VII.
Oh, you're saying that you just take. So VII is just x.
Yes.
Oh, I see.
Yeah.
Right. I missed that.
Yeah. So you have this one equal suppose you have the C of VII. Suppose your VI is a compact open so that you don't have to add a 0 here. So if VI just opens, then you have to only consider the you need to add 0 here. But anyway, yeah. Then what? VI G0 in this setting you don't have to.
But if you don't assume like if the VIIs are not compact, then you have to
add a 0 there. Yeah. So you have to consider C0 instead of C. Okay, so then you can consider like the castle. So that's a CIJL. That means you have a bunch of the multi-sections so that the IJ is in some IL, and your L comes from another index set F, for example. So that such that the CIJL, your IJ in IL is a multi-section. And the different L. Okay, so if the maybe let's give a name. So AL. Okay, so if the L is not equal L prime, then AL intersect. I don't think the intersect is a good one. So times AL prime equal empty. Okay, so that means the times the multi-sections from the different you times the bisections coming from the different multi-sections, so you opt trivial things. So just the empty set.
So it's an elementary groupoid, just a disjoint union of spaces, and then you have a homeomorphism between any two of these spaces, and it's just the so if it were in the case where it was just a disjoint union of points, then you'd have arrows connecting all the points.
But there's no connection between different multi-sections. There's no connections.
What the multi-section?
Multi-section is
The answer to your question, George, is yes. So for them, George was asking about the previous picture.
oh, okay. Oh, yes, yeah, that's true. That's true.
Okay, so
Yeah.
for an elementary groupoid, it's very simple. It's a groupoid, which is, you start with, well, you could start with an arbitrary groupoid and take the disjoint union of copies, and then you throw in isomorphisms.
Yeah, exactly.
That's not called elementary. It's called elementary if the if each of the pieces has no arrows except for the algebras.
That's true. Yeah, but
But that would have been too restrictive. That would have been too restrictive for the set.
What's too restrictive?
Like asking for like the components to be points.
Well, of course, but the point is that you're asking them to be spaces.
Yeah.
Well, okay, but that's the most elementary groupoid in the world. I don't know why it would take you so much time. I mean, you have a bunch of spaces and you have a obvious identity isomorphism between them, and that's your groupoid. And the algebra would be M and C of X. So
yeah, but actually you can.
This is obvious.
Yeah, that's that is why they call it elementary.
That's elementary. That's elementary.
Yeah, that's elementary.
But this should have been 30 seconds, not 5 minutes. And now 10 minutes. And almost elementary. Well, what's it?
Almost elementary means, okay, so then you have to add some non-trivial condition here. So groupoid is called so almost elementary. I just use a.
I really believe that someone should say something before writing anything on the board, because otherwise people are just frozen there. Okay, that's my. Say something and then write it on the board. But that should be a secondary operation.
So okay, anyway, so almost elementary simply means that you can use elementary groupoid to use the two castles. Okay.
And how do you put them together?
That's what I want to write here. So so you have two castles and the two castles, two castles. So in this setting, you have two castles here, C and D, and you have some extendability condition to use you have a compass set in the groupoid, and you want to use the compass set to times each bisections here, but the extendability means that what you obtain finally is still contained in the second castle.
Okay, but what's missing if you just have an elementary groupoid? Say two spaces.
No. In the same one. So
Sorry?
in the same groupoid, we can consider two elementary subgroupoid.
Are they disjoint?
No, they can have some overlap. So the point is that, so if you do some, I mean the compass set, I mean the priori given, so times any bisections, but it's still contained in the second tower, in the second castle.
Yeah, but suppose the two elementary ones both just have two sets, so you have two spaces.
Yeah, but
First space and the second.
but levels are still contained in the unit space, so that's the point.
Yeah, but you can't just give a very simple example that illustrates the things immediately.
Example, yeah, exercise. So, like suppose you do the integer action on the counter side, and by yeah, and then because then you can use like the Kakutani partition. You can do that, and you can make the shape as long as you want. And so let me write it. So let's use Z acting on C. So C is the counter side, right?
C is the
yeah, C is counter side. And then what we can do is that you can do the Kaptani-Rohlin partition, right? So for any okay, so you can find yeah, you can do the Rohlin power such that your SI is exactly 1 or maybe 0 to like the some m minus 1, but m is bigger than n, and bi are just some open set, and such that your C just equal some I in I, the SI bi, right? So that's what we can do. So this will give us a one castle, right? This is a one castle. One castle. So one elementary group point.
That's an elementary group.
Yeah, this induce some elementary group point.
The BIs are destroyed.
Yeah, BI destroyed.
They're connected by.
Yeah, this is Rohlin partition, right? Rohlin. Oh yeah, it just depends on the name.
I think if you're using the tower or the castle terminology, you have to use the tower as a terminology.
Yeah, it doesn't matter. Yeah, it's just yeah. Then so because SI is very large, right? You can choose the Foner part of SI. So for example, so given some K in your Z, it's a finite set. Okay, you can make your SI is large enough or Foner enough such that your G in K is bigger. Maybe you also give some epsilon. So 1 minus epsilon SI, you can do this, right? And this part you define the TI. So TI then BI.
Yeah, but I'm getting lost, but so you have, so far you have a single elementary groupoid sitting inside your group.
Yeah, so SI BI will give us maybe the first elementary groupoid. So we call it H1.
Okay, but you know, I'm getting sort of familiar with the terminology where you have towers and then castles. And usually in that point of view, usually the towers are disjoint. You have
Yeah, these towers are destroyed.
one tower, then another tower.
Yeah.
And then another tower, destroyed.
Yeah.
But that's a castle. And are you saying that's a disjoint union of elementary groupoids? Is it almost elementary?
No.
Well, it must be almost elementary.
Yeah. What I'm trying to.
Not the most general, almost elementary.
Yes, exactly. What I'm trying to explain is.
It's not the most general, almost elementary. If you take the single elementary, that's not the most general, almost elementary.
No.
It is almost elementary. You take the disjoint union of two, and they have a castle, and that's no longer elementary. But you're saying it is a case of almost elementary, where you have two disjoint towers. Almost, I guess it must qualify as almost elementary.
So suppose you only have two towers.
Yeah.
It is still an elementary groupoid.
Well.
Right.
That true?
So yeah, elementary groupoid just comes
We
from.
have to direct sum type,
Yeah, you that means corresponding some direct sum.
Disjoint union. It's a disjoint union of.
So this castle. Oh,
So an elementary groupoid then is the same as a castle.
yes, exactly.
Okay, so you said that maybe.
Yeah.
All right.
So this will give us the first castle or first elementary groupoid. H1 comes from the.
The most important part, we're going to have a collection sequence of castles, but the castles are allowed to intersect a little bit, right?
No,
No,
only two castles.
only two castles.
Yeah. So
What do you mean only two points?
yeah, I'm trying to explain here. So you have one castle here, H1. Okay, comes from this bunch of the towers, give you the first castle. The second one, you just change the shapes of the each SI, turn out to be the TI. What is TI? TI is defined in this way. You just take the Foner part of
Yes,
SI.
I'm completely lost. I'm sorry. But forget about castles, just look at single towers. Look at elementary groupoids that involves just a single tower. Then when you combine two of those to get
Let me give you this picture. Okay, so let our K is a finite set of the gamma. Gamma is a group, acting
These are
group.
connected.
Yeah. That's so this is S, the shape S.
Yeah.
This is the your base B. Okay.
And now,
Now you choose the T to be the G in K.
just continue with the picture, I can understand the picture.
Yeah. Okay. So the G inverse of the S.
Well, that's not the picture, I'm sorry. Where is the almost elementary group?
I'm trying to explain. So allow me to finish this sentence. Okay. So you choose a part of this. You choose a part of this is T. So the sub tower, a sub tower of this tower, so that if you times K times T is contained in S, so this is a almost elementary groupoid. The almost elementary groupoid is just like you can do extension.
But you haven't drawn the whole thing. You haven't drawn the whole. So the almost elementary group, you have the elementary groupoid there, which is the Rockland Tower, single, in this case, a single rock. And then you're saying, look at some of the blocks. Look at some of the.
Yes, some part of this.
Okay.
And I can make this T
What's
just
the new group? Where's the picture with the new groupoid? What is the new groupoid?
so in this case, the groupoid is just the all possible errors between these levels, right? And the second castle or second subgroupoid is just the part of this. So in this picture, just this one.
I mean,
Just
the
the
picture doesn't change. It's just the same picture.
yeah, actually, so the two castles here is just the one is contained in the second one.
It's not two castles, it's two towers.
Yeah, two towers. Okay, yeah,
The
two
one-
towers.
Okay, we said that you have a tower, then you have a sub tower,
Yes.
and that the system of considering the system of the two of those things, that's called almost elementary.
Yes. If you
What's the actual groupoid? What's the actual groupoid when you consider the two together? What are the objects? Are the ones are the subgroupoid things are those counted twice?
so in this case,
No, they're counted twice. The sub ones are counted twice.
yes.
Well, then that's
No,
the
no.
same as taking the disjoint unit.
No. That's not count.
Well, I like to
Count
see what the
twice.
You haven't said what the groupoid is.
So in this case, the groupoid is just the first tower, the larger tower.
Yes, and what's you mean that's the groupoid?
Yeah.
That's your.
You
that's-
treat it as a groupoid.
Well, it's an elementary groupoid, but you're saying it's also an almost elementary one in some funny way that I have no understanding.
Yeah, because elementary is definitely almost elementary, right?
What?
The elementary groupoid is definitely almost elementary because you don't have to
But
allow.
it was almost elementary before you drew the subgroupoid. It was elementary, and in particular, almost elementary, before you drew the T things.
Yeah, well,
Before you drew those.
yeah, because I want to explain. So what does the almost elementary means? It means you can find
Yes,
two castles.
But I'd like to see what the groupoid is that you're calling almost elementary.
Yeah, so yeah, I could.
It can't be just the original tower. It can't be just the original. I would understand it if you were counting the some of the objects twice.
Yeah, you can think in this way.
Well, but that's the same as taking the disjoint union, the abstract disjoint union.
But this is only for this example. In general case, we
Well,
cannot do that. right?
I go back from example. I like to go from example to example.
Okay, so but like so, if your space case not of
But-
zero
but by the way,
dimensional,
If you take a disjoint union of these two things, the two towers, the original tower and the sub tower, you consider the disjoint union. Well, then you're saying that in fact is also an elementary one because direct unions, disjoint unions are allowed.
but if you want to take this, maybe
Yeah.
draw a picture here,
Except
yeah, but then you cannot have this one. That's what we want. So
I
you
don't understand that equation. What does it mean that the K times T?
the K is a subset of the gamma. T is
What's that?
S is the shape. It's also the a finite set of the gamma.
Yeah.
And the T also is a finite set of gamma. So it's just some equations in the group.
You know,
So the point for the almost elementary is that you can do extension within two towers, or more general, within two castles.
What are you extending to what?
you extend T to S.
Okay, but and would you mind saying again what the new groupoid is that's called almost elementary? What is the actual groupoid? What are the algebras?
You
Well,
mean,
there's no new groupoid being built. It's a property. We're defining a property of a groupoid.
yeah.
It's almost elementary.
That's
Yes.
elementary. And the requirement is that you have two castles
Yes,
inside of it.
Yes.
That what?
such that you can, given some priori compact set, you can do the extension of the smaller one to the second one by this compact set. So that's what we did here.
Using the tower. So
Yeah.
there's like a small castle and a big castle.
Yes,
And you can extend the partition coming from a small castle to the big.
yes. Broadly speaking, yes.
All right.
And are the algebras the same?
I don't
Of the two castles.
I don't think.
Okay, well, to me, it's still a bit mysterious, but. What are the, it's, when you've got a theorem, and you're saying that in fact the hypothesis might, you don't know, there's no obvious counterexample to the hypothesis. So.
Well, no, we have
I
a.
think there is, but it's called.
Well, that's what I said, no obvious.
No, obvious.
So actually, so there's a very concrete example. So concrete example. So a
Well,
allosteric
Okay,
action.
but what I was gonna say was, maybe the definition will come out most clearly when we see the proof.
So you mean the
Okay.
proof of this theorem?
Well, yes, I mean,
Oh, it takes maybe
well,
at least 6 pages, I believe.
okay, but
It's like in
how
the
many did, 15 days or what?
6 pages.
Six, I mean, at least 6 pages because I forget
Okay.
I forget it in detail. The proof is written by me at this
Okay,
moment.
but in 2 hours, you had time to go through 6 pages, by the way, but if I might say. But anyway,
You have to do.
my point is that sometimes when one sees at least an outline of a proof, then the technical things that are assumed in the statement often are revealed in a more subtle way than just struggling to formulate a formal definition. Is that clear? Do you agree?
Yeah, I agree, but I don't think that can be done. I mean, in a talk because it's too complicated to write it down because it's, you have to do some
Okay, but then still, the difference between almost elementary and arbitrary is, it seems to me that this is what the interest of the theorem somehow depends on. Revolve on it. And it would be, it'd be interesting to see an example for which the theorem does not hold, the theorem is false. What is this example?
the example. So it's called the allosteric actions. So
What kind of?
allosteric actions. Allosteric.
What's in the name?
No, that's not somebody's name. It's
Okay,
that means so you are
that's Greek. Okay.
yeah. So it means that your action is in the algebraic series sense is free. So no, it's free for some given measure, but it is not topologically free.
All right.
Yeah, but almost elementariness essentially means essentially implies that your action or your groupoid is topologically free. So such action cannot be almost elementary. And recently, Marshall Joseph.
Just let me repeat that. If it's if you're assuming topologically, or you're not assuming topologically free.
Because this one implies your groupoid is topologically free, so you don't have to add here.
But that's not sufficient. The theorem is not true if you just assume topologically free.
No, it's still right.
Huh?
No. I mean, you need the.
Because this notion implies.
Free is not enough for the theorem to be true. You need the almost elementary.
Yeah. So that means you can add the topological freeness here, but it's the abundance.
What you need is also measures theoretically free with respect to certain measures.
No, that's not good
Well,
enough.
I thought that's what you said.
No, what I said is
In explaining this allosteric.
so this means that so your action is maybe the action alpha is free with respect to some measure.
That's what I said. Just now. Okay, then we agree.
Yeah, but not topologically free.
Well, I thought that's what I thought that's what I said.
Okay, yeah, that's the definition here.
That's good.
Yeah, but because almost elementariness implies your groupoid is topologically free. So, but this action is not topologically free. So even it has many other good properties, but it cannot be almost elementary.
Okay, will the algebra not be Z stable?
We don't know. So yeah,
Because it's,
in some cases it is stable.
But it seems to me it's irrelevant if it's whether it's measured theoretically free or not.
No, but
It's a counterexample. Look, if you have something which is not almost elementary, and the conclusion of the theorem is in fact false, then it's a counterexample.
be interesting.
yeah, actually, yeah, if you want, so any not topologically free action is a counterexample to the almost elementariness.
Well, we'll talk about counterexamples in the theorem.
The theorem? No, yeah,
So you're saying that among these ones which are not topologically free,
uh-huh.
of course, if something is not topologically free, then it's not covered officially by the theorem. Certainly. But, if you're looking for a counterexample, well, it might even be topologically free. A counterexample might be topologically free and just not measure theoretically free.
Uh-huh.
But this is strange. Your counterexample you're talking about is measured theoretically free, but not topologically free. That's a completely different kind of counterexample.
Yeah, that's kind of unfair because if it's not topologically free, then it's probably not going to be simple either, right? Yeah. Right.
Yeah, no, it's not simple.
Then it's kind of unfair to have that as a counterexample.
Well, yeah, what I was saying is that it is a counterexample of almost elementary.
Well, you're talking about a simple.
But then you could
You're
have.
talking about minimal. Is this minimal? Is the counterexample minimal?
Oh, sorry, no, sorry. Wait. I make a mistake about definition here. It should be topologically free, but not the free with respect to that measure. So
Oh, okay, well, I was starting to, that rings a bell, okay.
but not mu free.
Okay.
Yeah. But he showed that almost elementary also implies mu free.
Do you have an example which certainly it has to be topologically free for the anything like the theorem to be to apply. And the difference between topologically free and almost elementary is somehow measures theoretically free. In some sense, it's measures theoretically free and with respect to certain measures, invariant measures.
Yeah, sure.
All invariant measures.
No, yours is just given choose one. Let's choose one. Yeah.
So, well, okay, but if you want the theorem to be true, then it has to be free with respect to all invariant measures.
You mean this theorem?
You want,
Yes, because almost elementary implies mu free for all mu, right?
Yes, correct. Yeah.
okay, and is it difficult to visualize such an action which is topologically free, but not
It's just a profinite action, but from a rest product
Wait,
of
for a
groups.
finite action, do you mean what's a profinite action? I know what a profinite group is.
Yeah, exactly what you mean. So
What's
in that
exactly
sense,
by a profinite group?
yeah, you have a residue finite group, then you consider the profinite compilation. It's just that. Yeah.
Uh-huh. But what is it? But what happens to the space? Like if I have a group and I take its profinite completion, can it still act on the same space?
But you have to change something. You cannot take a normal subgroup to construct your profinite action, but everything others are same. Just use the call set tree and to
Oh,
this the call set tree give you a counter side, and the translation on each level give you the action.
Are you saying that your counterexample is a group?
Counter example is an action construct from a group, from a relatively finite amenable group.
And what does it act on?
Hmm?
And did you say what it acts on? What the group acts on?
The group can be it's a rest product. You have a
Wreath product.
rest product,
Wreath.
a wreath product. Okay, anyway, so you have a I actually forgot. It should be something like that. Yeah, it is a building group. So
Okay.
yeah, it's a yeah. I don't think torsion free is important. So anyway, so any a building group, and you consider such a risk product. Maybe you can use the I forget the detail. But anyway, so then you consider the call set tree of this guy, and on each level you just use the translation, and this will give you an action. And such an action is, of course, you should be careful by choosing your call set. So
Okay, so when you're checking the theorem, when you're proving the theorem, one can sort of imagine that topologically free is important. But is it possible to explain briefly why measure theoretically free is important?
you mean this theorem?
Yeah.
No, we do not use any measure free. But the fact is,
come on, the counterexample does not the counterexample doesn't satisfy that hypothesis. So the question is in the proof, where does the proof break down because of non-measure theoretic freedoms? I'm asking an elementary question.
yeah, but in our proof, we assumed almost elementary.
Yes, but that's
But the counterexample means that such action does not satisfy this, so you cannot use that.
well, no, but maybe there's a subsidiary theorem which says that if you assume it's topologically free and measure theoretically free, then maybe it's maybe forget about almost elementary. But suppose you say that you want your action to be topologically free, and you also want it to be measure theoretically free with respect to any invariant measure. Then is there a chance that that's a theorem? Then?
At this moment, I don't think at this moment I don't know.
Well, of course not.
Yeah.
I mean,
You have to assume some power structures into prove such.
well, look, it takes 2 hours to decide whether something like that is actually strategically necessary. I'm asking prying questions that are trying to get at the structure of the subject. But then I don't expect an immediate answer.
Yeah, maybe that's possible. Maybe.
I have questions that don't have an immediate
Sorry?
answer. If it doesn't have an immediate answer, it's better to ask the question after the talk, right?
yeah,
We are after.
And that's, I know.
But I would like to point out that like an example of a challenge with groupoids and amenability is that so for groups, if you have. But for groupoids, it's a bit harder to build polar sequences. Right,
You're right. Yeah, and in the groupoid case, so you are always we have seen that in the source fiber, there's no homogeneous geometric structure there. That's no longer a copy of a group. So
at the moment, various kind of freeness properties or amenability properties, it's not really known if they imply the existence of certain towers that we might want to have. And it makes it challenging. So these sort of assumptions of having certain towers from the beginning are important at the moment, because otherwise it's not clear how to structure the group. In the measure settings, I think things are better. I mean, the measure-wise amenability does have polar sequences. let's let's eventually.
Yeah, thank you. Yeah.
Which,
I would say let's thank you for the theory.
well, I don't know if we like the theorem all that much, but
Oh,
the work is very important. Someone has to do it.
well,
If I don't have to do it, then I can do it.
you don't. This doesn't apply to the groupoids as you see them.
No, it does, but it's kind of like, I would like a better theorem.
Well, how about the measure theoretically variable? Even that,
We'll wait for a better.
okay, but, well, all right, be nice to know what your criterion, more about your criteria.
Well, so as I said, so I would want something like, sort of like you are saying, so I in the almost elementary, you are asking for the existence of certain towers, of certain properties. And it would be nice to have a condition that doesn't talk about the towers
Well, like, how about-
directly, but then just
three,
produces them.
How about just measures?
Well, if that would that would be a better theorem.
Well, and anyway, this is presumably quite recent. Did you put it, you didn't put a date?
Date. Well, it's still archived, so it's the final version actually has not come, so it's under reversal. So, but the date is 2020. So yeah.
I was more excited for the methods, but maybe you shouldn't talk about the methods. I forgot, did you use your course geometry in this theorem?
Not directly, but under under the preparation you have to use that. Yeah.
Are we going to see more about the proof, 6-page proof?
Well, if you just want to explain that 6 pages, you have to do a lot of other works. You know,
No, for next time, I guess we're covering the ample group.
Oh, we don't have to.
We don't have-
That's just motivation.
But I wanted to hear about the geometric method, and I didn't get to hear about the geometric method. I'm still dissatisfied.
Okay, well, you inserted an interpretation of that, it might involve course development.
Well, no, because I read some options.
Oh,
already.
You can come to me
Yeah,
anytime.
yeah,
Yeah.
You're here for 6 months. Right, yeah, so next week we have 2 more hours of Shinmai, and then on Thursday we have Shuang talking about spatial nuclear dimension.